When a digital platform experiences a massive traffic spike, the system is immediately tested along two separate vectors of growth: scale, the sheer volume of data being ingested, and speed, the latency of executing a specific query. For decades, the standard response to this pressure relied on relational database management systems. These architectures utilized rigid schemas, mapping data into tables, rows, and columns. When traffic increased, the solution was straightforward: buy a bigger, more expensive server. This strategy, known as vertical scaling, eventually hits a physical ceiling. A single motherboard has a fixed limit for processing power. RAM slots eventually max out, and the speed at which a read head can pull data off a disk cannot exceed the underlying I/O bandwidth of the hardware. To process modern workloads measured in petabytes, engineers have to look past the relational model. Instead of upgrading hardware, they manipulate the physical storage layouts of the data itself. System growth eventually ceases to be a mere procurement exercise and ultimately becomes an exercise in structural physics. Relational databases are built on strict ASID properties, ensuring every transaction is processed reliably. To maintain that consistency across complex table joins, the engine must lock the data into a single shared memory space, tying the entire operation to one host machine. This centralized architecture creates a singular choke point. The moment the velocity of incoming data outpaces what that specific motherboard can process, the entire database fails. No SQL databases bypass this constraint by trading strict ASID properties for the base model. This stands for basically available, soft state, and eventual consistency. By accepting that data might be temporarily inconsistent across a network for a few milliseconds, the base model allows engineers to splinter the dataset and distribute it across a network of separate machines. Every architect must navigate this trade-off. You can prioritize absolute consistency on a single server, or you can maintain high availability by distributing the workload across a cluster of commodity hardware. Distributing that workload is known as scale-out, or horizontal scaling. Instead of upgrading a single machine's components, you add more standard nodes to the network to bypass hardware limits. Document-oriented databases like MongoDB accomplish this using the BSON format. By encapsulating all related entity data inside a single nested document, they remove the need to link data across multiple tables. The record is self-contained. This illustrates sharding. A central router block using a shard key divides the data payload across multiple shards. To ensure high availability, MongoDB uses replica sets. The primary node duplicates its data packets to standby secondary nodes. If the primary fails, a secondary takes over. Through sharding and replication, the database is no longer a single physical machine. It is a logical cluster capable of expanding horizontally to meet demand. While a primary-secondary setup provides high availability, routing all writes through a single primary node still creates a ceiling for high-velocity ingestion. Apache Cassandra solves this by implementing a masterless peer-to-peer architecture. By removing the central master node, Cassandra eliminates routing friction. Every node in the cluster plays an identical role, meaning any individual node can accept incoming read or write requests directly. This creates modular, linear scalability. If a 10-node cluster handles 100,000 writes per second, adding 10 identical nodes will yield exactly 200,000 writes per second. Scaling out a system effectively requires removing specialized routing hierarchies and ensuring every node shares an identical architectural role. Adding 100 servers to a cluster solves the volume problem by providing immense storage capacity, but it does not inherently make a complex analytical query execute faster. This shows a row-based relational table. To calculate average salary across 1 million users, the read head drags horizontally across the entire record. It is forced to pull name, age, and address data into memory just to reach the salary value, wasting disk I/O. To solve this seek latency, engineers use wide column stores, organizing data into column families. By rotating the physical storage layout 90 degrees, the data is grouped by attribute. The query engine drops straight down the contiguous salary column, entirely bypassing the irrelevant name and address blocks. This structural shift offers a secondary engineering advantage. Since all values in a single column share the exact same data type, They can be compressed using lossless algorithms, drastically shrinking the physical footprint. Query speedup is physically dictated by how closely the disk's data layout matches the query's specific access pattern. For executive dashboards tracking years of corporate history, scanning even highly compressed columns dynamically can be too slow. Relational OLAP, or ROLAP, attempts to handle this by translating dashboard clicks into complex SQL queries at runtime. But executing nested joins and group by calculations on the fly consumes immense CPU cycles. Multidimensional OLAP, or MOLAP, bypasses runtime calculations entirely. It trades load time for read time by running the math during the data ingestion phase, long before the user asks the query. This visualization shows the structure of a MOLAP cube. The standard 2D flat star schema extrudes outward to form a multidimensional grid. Every possible intersection of data is pre-calculated and stored at specific coordinate nodes. This architectural trade-off delivers near-zero query latency, but it introduces the sparsity problem. Because the system calculates every combination, intersections with no underlying data remain in the cube as empty cells, bloating the storage footprint. Absolute analytical speedup requires sacrificing dynamic flexibility and storage space in favor of hard-coded, pre-calculated answers. Physical storage layout is critical, but speedup is also governed by the dimensionality of the index mapped on top of that data. A standard database index, like a B-tree, is one-dimensional. It sorts alphanumeric strings in a straight line. If you ask a B-tree to query geographic coordinates varying across two overlapping spatial dimensions simultaneously, an x and a y-axis, the linear index fails. Geographic information systems, using spatial databases like PostGIS, exist to solve this specific math problem. A common use case is a radius search, such as an application looking for all available drivers within 2 kilometers of a user. This visualization demonstrates an R-tree spatial index. The database groups nearby spatial coordinates and encapsulates them inside minimum bounding rectangles. When the circular search radius expands, it checks only for intersections with these bounding boxes. By evaluating the outer rectangles first, the query engine instantly discards millions of irrelevant coordinates without ever scanning their individual data points. Complex, nonlinear data requires geometrically native indexing structures. Applying a one-dimensional index to a two-dimensional problem guarantees system latency. Managing system growth is an exercise in architectural alignment. You cannot solve a data ingestion bottleneck by writing better SQL, and you cannot solve query latency just by buying more hardware. This chart maps database architecture against the two vectors of growth. The y-axis represents the hardware strategy, from scaling up a single server to scaling out across a network. The x-axis represents the data structure, moving from row-based tables to columns and cubes. Traditional relational databases sit in the bottom left. They provide transaction consistency, but rely entirely on single machine scale-up and row-based storage. Document stores like MongoDB move us up the y-axis. By using flexible schemas, they allow for massive horizontal scale-out across distributed networks. Wide column stores like Cassandra shift us across the x-axis. They combine modular scale with contiguous column storage for high-velocity sequential write speeds. And on the far extreme right, we find MOLAP arrays, trading dynamic flexibility entirely for the absolute read speed of pre-computation. In modern computer science, your data is only as fast and only as scalable as the physical architecture you engineer to hold it.